All right, so what we have here is we have a Stanley Meyer resonant cavity. We have a reservoir tank, return tank. We have a power supply, a ppm meter, control for the power supply to control the pump, a variable speed pump, flow meter not hooked up, control valves which switch the flow between going into a deionizing filter or bypassing it. So one of the first objectives for this demo setup is to experiment with and try to understand the impedance characteristics of this thing with different types of water flowing through it and in it. And the way that is done is using an LCZ meter. And with this meter, I am able to set it to different frequencies to test that, up to 200 kilohertz, I believe. Yes. All the way down to 40 hertz. I think it's 40. Yeah, 40. It gives me the capacitance value. I'm going to set it to 5 kilohertz. 2.2 nanofarad. It tells me the resistance, which is 517 ohms. This cell has been sitting for a while, overnight, and it has some contaminants in it which have lowered the ohms. If we were to look at the impedance, it's riding pretty much the same ohms with a phase angle of -2, meaning most of the power in this cell right now is real power, and it's not going into the capacitance. It is passing as real power. Alright, so I have this water fuel cell. It has been sitting overnight and has not been messed with. Water has not flown through it. I'm getting ready to make water flow through it by activating the pump. But I want to show, it seems water has not been flowing through it, that the impedance is pretty low at 513 ohms with a theta phase angle of -2 degrees. And this is at 5 kilohertz. So as I turn this pump on, I'm pretty sure the resistance is going to climb and the phase angle should increase in the negative direction, indicating that more power at this frequency is shifting into the reactive component and out of the real component of the water fuel cell. So let's see. Let's start it now. It jumped up to 1 kilo ohm. I'll let it flow for a little bit. We're at -5 now, and still at 5 kilohertz. So the water technically is at 1.3 K impedance wise, but if we look at capacitance, we're sitting at 2.2 nanofarad, dissipation factor of 11, resistance of 1.28 K. So I have the water fuel cell pumping right now. It's not pumping too fast, but it's pumping. Currently it's reading 1.24 kilo ohms with a phase angle of -5. Capacitance is at 2.2 nanofarad. So I want to point out here that whenever you increase frequency for a capacitor, the reactance is going down in ohms, and it goes up when you increase frequency. So for it to go down means that the power should start to shift into the reactive component when I increase the frequency. So this number, where is it at? This number here should start to go more negative as I increase the frequency, indicating that more power is going into the capacitance of the cell rather than passing as resistance. So now at 10 it's at -9. 12 kilohertz is at -11. I'm going to go up to 50 kilohertz we're at negative 40 degrees. Almost half of the power now is being stored reactively rather than being passed resistively. If I bring it all the way up to 200 kilohertz, we're at negative 73. So to be at negative 90 would mean that all the energy is going into the reactive part of the cell, meaning capacitance. So the higher you go in frequency, you're able to adjust the phase angle of the cell because the cell has an inherent resistance. And it's a ratio between the contaminant resistance and which I don't know if it's considered ESR, and the frequency with relation to the 2.2 nanofarads of the cell. So at 200 kilohertz, we're at a Q factor of 3 for the cell in this situation. All right, the water fuel cell is still pumping. We're reading 1.2 k ohms, negative 4 phase angle. So in this demonstration, I am going to adjust the valves over to pump into the filter, and we're going to watch the change of resistance within the cell on here as I do it to show how high the water can climb in resistance and phase angle with relation to being still set at 5 kilohertz. So I am turning on the filter now, and I am turning off the recirculation. We have jumped up to 12 kilo ohms through the deionizing filter and up to a phase angle of negative 68 and climbing. It's still filtering out the ions. I'm going to speed up the pump. So the cleaner the water gets, the more it'll perform as an ideal capacitor. The capacitance stays the same. It just becomes more ideal and less like a parallel RC circuit. So the DI filter has been running for a little while through the water fuel cell. Currently it's sitting at 2.3 nanofarad with a Q factor of 0.03 at 40 hertz. The impedance is at 59K with a negative 2 degree phase angle. So at 40 hertz, the reactance value for capacitance goes up, meaning the resistance goes up to try to store energy in the capacitance. So it makes it harder. So most energy ends up being passed as real in this situation. As I increase the frequency, I want to watch the phase angle increase and this decrease. So I went to 50 hertz, 60 hertz, 100 hertz, 120 hertz, 200 hertz, 400 hertz, 800 hertz, 1 kilohertz, 2 kilohertz, 3 kilohertz, 5, 10, 12, 15, 15.7, 16, 20, 22.2, 25, all the way up to 100 kilohertz. We're pretty much totally reactive now. Barely any energy is being passed in the resistive part of the water. It's acting like a capacitor. 200 kilohertz, pretty much a pure capacitor, ideal capacitor. Having a this cell having a impedance of 368 ohms at 200 kilohertz, with water that is being processed constantly before it makes it to the cell. It's just recirculated over and over again. still at pretty much 2.2 nanofarads. In this situation, the dissipation factor is very low. Resistance 50K. Q 138. So this 50K is very high. That value is the actual parallel resistance within the cell with the capacitor. It's because the water is being filtered constantly. It's riding this. If I switch it over and I start turning on the other one, we instantly drop off. If I turn the DI all the way off, now we're recirculating the water that we've been running in the filter constantly, and it's dropping off. It's at 22K. It's at 20, 19. We're still reading 2.1 nanofarad. I'm going to bring the frequency down to 5 kilohertz. 16K, 15K. The water's still pumping. The only thing I could think to why this is happening right now, to why it does this, is because I have an open container that can allow ambient gas ions possibly to reabsorb, maybe CO2, I'm not sure, to reabsorb and create more conductivity in the water, just normal gas ions. Still writing at 2.1, 2.2 nanofarad. The water's circulating and we're still dropping. Water's been circulating for a little while. Still dropping. So if I touch the water, let's see if it affects it. My finger, just the contaminants on my finger. I stirred my finger in the water, and look at that. What happened there? Just stirring my finger in the water. We're falling off even more. We're at 4 kilo ohms. We were at 50 with the DI filter running constantly. Open container, circulation, touch my finger to the water. We're now at 4K in the water and drop it. All right, this is to explain that just because my finger touched, that when you set it to lower frequency now, 40 hertz, we're reading 11 nanofarads. So the capacitance has jumped by what, 5-fold. This is because my finger had electrolytes on it. It had salts, had things that add conductivity to the water in such a way that also adds capacitance to the water, just like an electrolytic capacitor will do. I am adding electrolytic capacitance into the water. It shows up more at a lower frequency because these ions within the water have more of a chance to reach the electrodes to create the countercharge for charging the electrode. Therefore, they're more reactive in showing up as a phantom capacitance, which is more or less electrolytic capacitance. But if I increase the frequency, it starts to disappear. The reason why it is disappearing is because the ions are being taken out of motion. These ions are being taken out of motion at a higher frequency to where they cannot provide countercharge in a sense that shows up as reactive charge within the circuit. So here I want to show that once I turn the DI filter on, I'm at 40 hertz. Once I turn the DI filter back on and turn the recirc off, it will drop back to 2 nanofarads because the ions that my finger put in the water will be removed. So it takes a little bit, but the water will stabilize. Once the ions are removed, this number will stabilize for 40 hertz, back down to 2 nanofarad. So this is what is happening, is we're removing the electrolytic capacitance that the ions can provide when they're in the water.